Hi everyone, in this video we're going to talk about different types of nuclear decay and different types of non-natural nuclear processes. So let's go ahead and look at our different types of nuclear decay. So I'd like to examine this graph to start with. So you'll see here on our y-axis we have number of neutrons, and over here on our x-axis we have number of protons. So essentially this graph is showing you the character of different types of atoms. And we see outlined here are types of decay processes based on where these atoms fall on number of neutrons and number of protons. Our legend here shows us that the black dots are stable nuclides, i.e. stable atoms, ones that aren't going to undergo nuclear decay. So in the center here, these are our stable atoms that aren't undergoing nuclear decay. Now what you'll notice is there's kind of like large swaths of color on this graph, which is really indicative of something. One thing you'll notice is up here in this region, we tend to have a lot of yellow, which is our alpha decay. We had discussed how this is a helium nucleus, how it's helium 4, 2 plus. So what this graph is showing us is that atoms with a large number of neutrons and a large number of protons tend to undergo alpha decay. So what you'll notice is that's our heavier elements. So on our periodic table, elements that are 83 bismuth and heavier tend to undergo nuclear decay. Okay, so all elements with a mass greater than or equal to 83 are radioactive and can undergo radioactive decay. Because of their weight, their nucleus is just unstable, and so they tend to emit things like alpha particles in order to reduce the number of neutrons, reduce the number of protons, because we can see that that happens here. Whenever a helium nucleus is let off, we lose 2 neutrons and we lose 2 protons, which is a very effective way for an atom to decrease its mass. Now, something else you'll notice about this is outside of our black line, we tend to have a blue section on the left and an orange section on the right. So the blue is what's called our beta emission, or beta minus. So beta minus, all right. And beta minus is a type of radioactive decay that allows us to reduce our number of neutrons. So our atoms that tend to be neutron heavy, or an isotope that tends to be neutron heavy and wants to reduce its number of neutrons, tends to undergo beta decay in order to reduce that. Atoms that tend to be on the other side, or isotopes that tend to be on the other side of our stable nucleus center here, we're seeing that they have a high number of protons in relationship to their neutrons. So they tend to decay via a process called beta plus, or you might hear it called positron emission. We're going to go over all these in detail. But you can see that what it allows it to do is it allows it to reduce its number of protons and get closer to being a stable nucleus. That's the goal of all of this radioactive decay in the first place, is you have an unstable isotope or atom, and its nucleus is just not stable, and so it emits things. It changes its composition so that it is stable, and it does this through a radioactive release of beta particles or alpha particles. So I just want to be really clear here that radioactive isotopes are usually not very abundant in nature. So 1 out of every 8,550 potassium atoms is a radioactive isotope of potassium called potassium-40. So we don't readily encounter these isotopes in nature. They're very low percentages. So you can see here that carbon-14 is 0.00001% of all carbon atoms. So encountering these in nature is very rare. There's going to be a very small amount of them. The only time you encounter a lot of radiation is when it's being concentrated, usually from humans. So humans can concentrate radioactive elements. We do that in the form of nuclear power plants, and we do that for nuclear weapons as well. So just to be clear, in nature, there's not too much of this going on. So something I wanted to go over is we can actually predict what element or what isotope an atom gets formed whenever some type of radionuclide undergoes nuclear decay. So we had looked at our alpha decay, which is a loss of a neutron and a proton, because it's He42. And so what this means is, say you start with uranium. Uranium, let's look at 238, 92. Say it loses a helium. It emits a helium, 4, 2. What this means is we form a new atom, which has 4 less mass and 2 less protons. So our new number here is 90, because it's 92 minus 2. And our new mass here, we've lost 4 in mass, because that goes to the helium. Remember, it's splitting. And so we're seeing that this is 234. So the question is, what would this new element be? Because we have a new number of protons, and anytime we change our proton number, we get an entirely new element. So we'd have to go to our periodic table, and we'd have to find uranium, which is way down here, and we need to find the one that has 90 protons. That's thorium right here. So our new element is not uranium, but thorium. So what we've made here by emitting an alpha nucleus is thorium. Thorium-234. The natural mass on thorium here in the periodic table is 232, so this is an isotope of thorium. That's what's made through our alpha emission. Now let's look at the other types of common decays that occur. So the next one is our beta decay, or beta minus, as I like to call it, because we note positrons, this here is beta plus, this one's beta minus. You'll hear me call it multiple things. Okay, or you might just hear beta decay. Okay. So from our alpha decay, we had seen that we had a new number of protons, and we had a new mass. Let's take a look at our beta decay. So beta decay is when you lose an electron. Now that might not seem intuitive because we're talking like neutrons here and protons here. So what do electrons have to do with it? What this does is it gives the atom more energy and allows it to convert a neutron to a proton in order to make it more stable. So we're seeing that these neutrons, so it decreases neutrons, and it turns it into a proton. But what we're seeing here is that the mass of the thing stays the same because electrons have no mass. And we're converting a neutron into a proton, and neutrons have the same mass as protons. So effectively, there's no change in mass here. Okay, so beta emission occurs when a neutron changes into a proton, and it does this by emitting an electron. It emits, oh goodness, proton by emitting an electron. Okay, so what this looks like is we have some element. Let's use uranium for an example again. So uranium-238, 92, just because I'm familiar with that one. It's going to lose an electron. So the electron comes off here, and we form an entirely new element, okay? And remember we said that this one reduces neutrons. So what we're seeing here is that we gain a proton because it reduces neutrons, increases protons. So now we have 93 protons, and our mass stays the same, 238, because we aren't losing any mass. So we want to determine what element this is. So we go to our periodic table, we find 93, which is neptunium. That's an exciting name, okay. So if we wanted to write the chemical symbol for this, it would be NP for neptunium. And we're seeing that that happens when an electron is emitted, and this is what we call beta minus decay or beta decay. They're the same thing. So if you hear me say beta minus or just beta decay, it's the same thing. Okay. Now let's take a look at our last form of radiation that I want to talk about. There are more that I'm not going to discuss, but we're going to talk about these three. Okay. So this is beta plus decay, and this is positron emission. We're going to discuss what a positron is. Okay. And essentially what we're seeing here is for positron emission, we're seeing these are proton-heavy atoms, and so they're reducing their proton count to go back to a stable nucleus. All right. So it reduces protons. So a proton is converted into a neutron. And it does this by emitting what's called a positron, or an anti-electron, as I like to call it. So it emits a positron. This one here emits an electron. A positron is kind of like the opposite of an electron. It's called an anti-electron because it's kind of like an electron with a positive charge. So don't wrinkle your brain too much about that. I'm going to show you how we represent that as well. Do note when this nuclear decay process happens, we have the same mass. It's just like the beta decay where we're seeing that a particle from the nucleus is changed into a different particle from the nucleus, but overall the mass of the thing doesn't change. So during positron emission, this is our E+, we're seeing a proton change into a neutron, and it does this by emitting excessive positive charge, i.e. a positron. Okay. So here's kind of what that looks like. Let's use uranium again as an example. So if uranium underwent positron emission, where it emits a positron or an anti-electron, you'll notice here that the symbol we use for a positron is the same as an electron. We use E, but the charge on it is different. It's positive. It still has no mass, which is important. So this is how you represent a positron. Make sure you have that written down. Okay, so we're going to emit our positron. All right. And now we'll make a new element through this nuclear decay process. So what happens is this is for proton-heavy elements, so we're going to lose a proton, which means we go to 91. Mass stays the same, 238. So we'll want to go to our periodic table to find out the identity of this Y. What element is that? Here it's protactinium, which is represented by a Pa. That's the chemical symbol for it. So it's Pa238. That is an isotope. The mass of protactinium on the periodic table is usually 231. So this is an isotope of that element that's formed via positron emission. So here's a review of the three processes that we learned. So we learned alpha decay, beta decay, positron emission. Okay, so I'm going to hold you accountable for these three, i.e. understanding these notations here, the different ways that we can write them. This can be a positive, or you can leave it just a single one. This is called a positron. You might hear it called beta decay, alpha decay. So being familiar with these terms and being able to determine what's emitted here and how that changes your element. Like, does it gain protons? Does it lose protons? How to identify the names of the new elements after the nuclear decay process has happened. So here's what changes. Alpha decay is the only one that changes both your mass and your atomic number here. So it's very unique. Anytime you see a change in mass, it's probably going to be alpha decay in this class. And then here for beta and positron emission, we're seeing atomic number only change, which is the number of protons. Okay, number of protons, mass is number of protons and neutrons. Now I did want to bring your attention to other types of decay processes. So we're only learning these three. There are a lot more. There's a lot more going on. We just don't have time to cover it. There's such a thing as electron capture, where nucleuses are eating electrons. We have gamma radiation as well, which might be something you've heard about, which is just energy. There's actually no change in the identity of the atom, just energy is emitted. We have neutron emission. We have proton emission as well. This changes the mass of the element that you start with. So there's a lot going on. We can emit all kinds of different particles with nuclear radiation. You saw some of these on this initial graph that we looked at. In addition to these three types of processes, you also see there's neutron and proton decay shown here. It kind of happens right in here. There's some pink little dots down here for our proton decay and our neutron decay down here. So these are our more lightweight elements that are undergoing this. They aren't our super heavy elements. But again, we aren't going to talk about that in this class. Okay, so now it's time to test your knowledge. See if you can fill in the blanks for the following questions. I'm going to ask you to determine if this is alpha, beta, or beta plus decay, i.e. positron emission. Okay, so see if you can fill in the blanks to answer these questions. So for number 1, it says emission of a blank allows an atom undergoing nuclear decay to convert a proton to a neutron. So on our scale, that means, so if this is protons, and this was neutrons, these are going to be our proton-heavy elements. And this happens with positron emission, or beta plus. Emission of a blank allows an atom to undergoing nuclear decay to convert a neutron to a proton. So that's going to be on this side of the graph. That's our beta minus decay, and it does this by emitting an electron. Okay, so this emits an electron disappears, and this one, a positron, disappears in order to let the nucleus do its duty here to change protons to neutrons and neutrons to protons. And the last one asks us emission of a what allows an atom undergoing nuclear decay to decrease both its mass and its atomic number, i.e. the number of protons. This happens through alpha decay, and it emits a helium nucleus or a helium ion. You could call it that as well. Or you could even call it an alpha particle. These are all types of particles here. Okay, so any of those terminologies are fine. Alpha particle, helium nucleus, or helium ion are acceptable.